Newton's third law is just finding out where the forces are being applied. Okay? So, if for instance, I have a force in which I'm pushing on the wall. So if I consider myself pushing in the positive direction, then the wall is pushing back in the negative direction. Okay? Now the net force could be 0. I'm clearly not going to move the wall, but I may not move away from the wall as well when I'm pushing against it. Alright? So when we say an equal and opposite reaction, that basically means that you're going to have to figure out which sign are you switching. Okay? One of those two signs needs to be switched. So if you look at page 145, this cart question is a really good question for us because it allows us to see where the forces are being placed in each case and which one it has. So a pull toy consists of 3 carts joined together by 2 short strings and a longer string for pulling attached to the front of the cart. If a child pulls the toy with a horizontal force of 6 newtons, what force must each of the short strings be able to withstand? Okay, so the free body diagram looks like this. I have a cart at the end, a 1 kg cart, attached by a string in which I have a 1.5 kg cart, a smaller 0.5 kg cart, and then I have a force here pulling on all of it. That would be an applied force of 6 newtons. Okay. So, the first thing I want to find out is if the force is 6 newtons on this guy. What I need to do in order to find out what the force is on this string and this string, how do I find force again? Mass times acceleration. It's very simple, right? So if I have a 6 Newton force, I should be able to calculate what my acceleration is by finding out how much mass is being pulled, correct? So I have 0.5, 1.5 is 2, 2 and 1 makes 3 kg. So because they are all moving together, they have the same acceleration. Well, what is the acceleration on each cart? 2 meters per second squared, right? So now, this string right here is pulling on one cart only. So what is the force on that string? Well, the mass is 1 kg, and it's accelerating at 2 meters per second squared. So therefore, the force on that one string is 2 newtons. It's pretty simple. All right? So what's the force on this string then? Well, how much mass is this string pulling? 2.5. So 2.5 kg times 2 meters per second squared equals 5 newtons. Okay? So all that needs to be done by you is, can you find the acceleration of the carts? And because they are attached, we look at them as being moving in one piece, and then we break it up into individual pieces after that moment. Now we're going to get into questions with pulleys, in which we are looking at string tension, which is a force. And we have to consider it doing it the same way. Find out how fast they move, accelerate, not how fast, but how much they accelerate and move as a unit, and then you find the individual tensions after that spot. Yes, sir?
This is regards to it accelerating, but if it's going at a constant speed, will the
acceleration be 0?
So then the force will stay the same as the...
Yes.
Yeah.
There'd be no force.
No force. Well, that string still needs to carry some force, right, as it's going along.
Yes, but if there's no acceleration happening, you can't have any net force on it.
I guess, but there's still deceleration due to grades.
Well, deceleration and acceleration would be the same thing, right? As long as they're moving at a constant speed, you don't have any net force on it, it's zero. Okay, yes, I agree, there's gotta be tension there,
Yeah.
for sure. There's tension between the two, but as for force, which is tension, okay, with no acceleration, we consider it no force, okay? All right, how are we doing so far?
Thank you for the instructions. Jesse Roche to room 7, please. Jesse to room 7.
Now, so far we've found the amount of force on each of these strings here, right? So I'm going to call that one F2 and then F3 over here. Now, there's a reason I'm going to do this in a second. But this is going to answer your question right now, okay? So on the first one, there is 2 newtons of force on it. That's fine. There's no other force pulling back. There's no friction force in the question. So the only net force acting on this guy is 2 newtons. What about this guy right here? Well, we found the force F2 to be 5 newtons, correct? But what is the actual net force on this guy, if we were looking at 1.5? What is it? 5 newtons in the direction of motion. 2 newtons pulling it back. The net force on that guy is 3 newtons in the direction of motion.
Couldn't you just do 1.5 times 2?
Yeah.
Just that all the current is 1.5 kg, and then we know the acceleration is 2.
Excuse me again. Eric Scotian to room 16. Eric to room 16. And Mr. Quallen, please call 15,000.
Okay, say that again. So if you think then that,
If you just did 5 and take away 2, and could that just 1.5 times 2 meters per second squared?
you could,
Yeah.
which is what I did right here.
Right.
Yes. Okay? All right. I'm going to see if there's one more sample problem. I think there's
Christine, I
one.
have a question for you.
Yes, sir.
I get 2.5 kilograms on F2. You add the.
It's pulling both of these two.
Oh, okay.
Okay, so the mass is connected. This force is pulling the 2 masses right there. Just as this force right here is pulling all 3 masses. That's how I got the acceleration in the first place. Okay?
Yeah, that's not a very wise question to ask. but-
No, that's fine. Okay, that's it. That actually takes care of all of chapter 4. Newton's 3 laws. It's a short chapter. Alright, so for the remainder of the week we'll finish up a review. I'll try and get an assignment. The assignment I looked at yesterday was a little more than I wanted, so I have to break it down a little bit to get for you probably by tomorrow. But other than that, you should be able to work on the review. There's not a lot of review questions, not like the last 2 units. There are only 22 questions total in this one. So that's what I need you to work on today. I will answer any questions that you had. Yes, Cole?
One of the problems I'm having right now with this section, or this unit, is the different equations when it comes to the forces. Could we just go, like, draw?
There are basically only 2 equations you need to know. And actually, it's not even 2 separate ones, it's 2 that are together. Your net force is found in 2 ways. Taking your mass and times your acceleration. That's one way in which we can get our net force. Okay? So if you know the mass of something and you know its acceleration, you can multiply them and get your net force. The second way to get net force, and we generally put these 2 together in order to solve our questions, is take the direction of the force that the object is moving and subtract anything that is holding against it. So I'm going to write this for no other reason than just this means resistance. Okay? Most of the time that's going to be friction.
And what's
Some of the time it'll be another, sorry?
what's the number for friction?
It'll either be given to you or you have to solve for it. I'm going to get to that in 1 second. So anyways, this just means a resistance force. What's working against the motion? Okay, so for right now, all you basically have is friction. Maybe, like in this case here, this guy's working in the opposite direction, right? So that would be considered your resistance force as well, because it's working against that force there. All right? And then force of friction is found by taking your normal force times your coefficient of friction. And the coefficient of friction is given to you either on a table or in the question itself. Okay? So this guy is what it represents is the different surfaces. Each surface has a different amount of friction involved. Okay? So that's what the coefficient of friction is. The normal force is the force that the surface is pushing up on it. So we have to take that into account as well. Which basically is, in most cases, will be mass times acceleration of gravity. Okay? That's all that's new in this whole section, are those three things.
And then could you just draw a box and then put where each would kind
Yes.
of go?
Okay? Let's say that I have a box resting on a table. Alright? Your force of gravity is pulling that box down. What's working against it is what we call the normal force. So that's this guy right here. So the normal force works perpendicular to the surface. It pushes up on the box. That's why, for example, these sheets, they're not moving right now. They're sitting on the table, they're not going down, they're not going up. Gravity's pulling them down, force of the desk, the normal force is pushing them up. Okay? Now, if I apply a force, let's say I push or pull this thing in that direction, I consider that my applied force. The applied force is any force external force that I place on it. Now, in order for that to happen, I have to accelerate the box. Because if I push it at a constant speed, it's not considered to be an external force. All right? It's at rest. Or in constant motion, there's no net force on it. There has to be an acceleration. And then this would be your resistance force. Most of the time it'll be friction. Works against the direction of motion. Alright? So I did draw this of a skier the other day. So here's a skier that's going downhill. Okay? Gravity's pulling him straight down. The normal force is pushing him straight up, perpendicular to this line right here. So at a right angle to it. His motion is taking him down the hill, parallel to the hill. So that's FA. This would be considered FA right here. This is your normal force right there. Okay?
So
And
you
then
can't have two FAs?
your force of friction would have you moving back. No. For math purposes, I draw this triangle to solve it.
Okay.
Okay? But realistically, this triangle doesn't exist. These are the forces that are pulling and pushing on your skier. Okay? But using math, this triangle, I can solve for FA and FN over here as well. I can solve for those using a right triangle. We haven't got there yet. We get there next unit. But we're working towards this. Okay? So the key is Fn is perpendicular to your surface. Force of gravity is perpendicular to your horizon. Always straight down. Your applied force is in the motion direction. And force of friction will work against your applied force.
Okay.
And
So
that
it's
pretty
not
much covers your bases.
That's not as hard as I thought.
Okay, good. But that's it. That takes care of everything that we've learned on forces up to this point. And that's the whole section. Okay? Any questions from yesterday? Kelsey?
1 number 2A. I found the,
Alright,
I just needed the angle.
okay, yeah. Because you probably didn't draw it right. When we are adding vectors, we have to draw them tip to tail, right? Okay, so if I look at that 2 Newton force, okay, if I draw it, like in the picture, in the diagram, I've got it drawn right here, right? As 1 Newton of force. But the problem is it's tail to tail, which means I'm actually subtracting it. So what I do is I take this guy and I move him to the tip of this one. So I move him right here.
Yeah, and I do that.
Okay, so this is 60 degrees right here, right? Because this whole angle right here was 120. And what you're looking for is that vector force right there. So that's 60. This is a force of 1 Newton. Now use your law of cosines. Okay, so make a note of this if you haven't got there yet. On question 2, you don't draw these tail to tail. You have to take it, move it all the way across, and put it on the tip of the first one, which essentially is parallel lines now. So this angle of 120 is all on the outside here, which makes that 60 on the inside. So that's on question 2.
So that then wouldn't be really triangle.
No, it's not a right angle triangle. I need that angle right there now. Okay, yes, Rory.
So I did it the other way around, like I put the 2 Newtons on top.
Okay, so let's try that.
I still got the same answers, but what it, like other than
Okay,
the
so your
angles.
angle's gonna be different.
Other than the angles, yeah.
Your angle will be, okay, so if I draw it out, you did this one first,
Yeah.
right? So I draw this, draw this.
No.
No,
Other way.
other direction, my bad. Okay, so I've got this, that, over to here, like this is in here. So this angle here will be the complement of that angle.
That's, yeah.
And so when you look at in the textbook, if yours adds up to 90 degrees with this one, then you got it right.
Okay, yeah.
Okay? Yeah.
I don't know how to do 5 on page 1.
Okay, well let me finish with this first. Okay, are you okay now?
Yeah.
Alright, Rory, you alright?
Yeah.
Anybody else have questions about number 2? This one was the one that should have tripped everybody up in that book, in that so far.
For the right side.
Yeah.
That F1 Newton there.
Yeah.
How'd you get that?
That's this guy. I just moved him from here to here.
Okay.
Because I can't draw it tail to tail, Morgan. I have to draw my first one and then draw the second vector from the tip of the first one.
Okay.
So I take this guy in the direction he's moving.
Yep.
And move it to here, to the tip of the first one.
Why are we doing that exactly?
Because when you add vectors, it's always tip to tail. If I draw it like this, I'm subtracting the vectors. We don't do this.
You don't subtract vectors.
Well, we do, but we draw them in the opposite direction. We don't draw them tail to tail. Okay?
Okay.
So take this, move it to the tip of the first one.
Okay. And then, since you have moved the line, you'll have to add in the hypotenuse and then.
Well, it's not a hypotenuse because there's no right angle, but yes. This is
Or
from
along
here
the
to
side,
here.
yeah.
From here to here is my resultant vector. That's what I want to solve for.
So the part that I might mix up is whether to.
Let me do this different. Let me explain this a different way to you, okay?
Okay.
I've got a box. and I'm pushing on the box. And I'm gonna push the box in this direction. Okay?
Okay.
Now, somebody else is gonna come along, and they're gonna push the box in that direction. Okay?
Okay.
So the box is gonna be going a little bit this way, and then a little bit that way, and a little bit this way, and a little, you agree,
Mm-hmm.
right? So I got two people pushing on this box. So I gotta find out what direction is this box only actually gonna go. So I know it's gonna go this direction because of that vector, right?
Yep.
So I have to add on the direction of which this guy's pushing, which is this right here.
Becoming more clear now, yeah.
So it's gonna go this way, and then up, and then this way, and then up, and then this way. So it's eventually gonna end up over here somewhere,
Oh, I see, yeah.
okay?
Okay.
So that's how I end up with this triangle.
Yeah.
Is that better?
Yes.
Good stuff. All right. Sam, 5,
138.
138. Okay. The majority of you will have a difficult time getting this question correct. Okay? Because this is very similar to what we were doing in the kinematics unit. You have to take into account that there's two things that are occurring here. So in stage 1, for a distance of, I believe, 1 meter, there's a force being applied to a skateboard. So the guy jumps on the skateboard and pushes for 1 meter. At the end of 1 meter, he now rides the skateboard out. And so it continues on for a distance of what? 1.65? 25, thanks. 1.25 meters. So right here, there's a force happening. I'm pushing on the skateboard. That's a force. Right here, there's no applied force happening. What's happening?
Gliding.
I'm gliding. But how come I come to a stop?
So resistance.
Because of friction. Okay? So in this section right here, there's a force of friction. And that's it. So that's going to be equivalent to your net force. Right here, there's an applied force that is greater than your force of friction. Because you're pushing the skateboard along. So we have two parts that are happening here. So in part number 1, he starts from rest. How much time does he push for? Does it say?
8.5 seconds.
He pushes for 8.5 seconds.
And his mass is 0.5 kilograms.
Skateboard.
Okay. And you said his mass is 0.5 kg of the skateboard, right? Okay? So what is it that I need here?
Acceleration.
I need acceleration, and what else do I need?
V2.
V2. Because V2 is going to be whatever that velocity is at that point right there, right?
Yeah.
Which is going to be my velocity 1 here. My acceleration I don't know, my time I don't know, my mass, still 0.5 kg. What is my V2?
0.
Comes to rest, right? Okay. So, if I were doing this question in Unit 2, I'd find my acceleration, I'd find my V2. Then I'd use my V2 as my V1 here, and find my acceleration, right? I fill in all of the blanks that I need. So let's do that first, and then I will bring it back to how does this affect force. Okay? So first thing I want you to do then is find out what A is here. So I have dV1t and A. So okay, so I've got distance here. I've got my time here, this V1 is 0, right? So I got a half times time squared. So take 8.5 square it, divide it by 2. What do you get?
36.45.
Okay, so now take 1 and divide that number.
0.027. Oh, uh-oh. 0.0.
0.277 meters squared. Second squared. Okay, good. Okay, so that's my A right now for this. What do you suppose I'm going to use that A for eventually?
You decelerate.
Find what?
Decelerate.
Nope.
5v2.
Nope. What am I going to use it for?
Your force.
Which force?
Your
No, not yet.
net force.
I'm still in the first section, right? It's
Net
my net
force.
force. Okay?
Good
So
job.
I'm going to use this A as part of my net force. For right now, I'm just going to leave it. Okay, I need to find V2 now. V2 is equal to, I've got T, V1, D. So I could use velocity average to get that. So what is my V2? I'll write that out, sorry. Delta D is equal to
0.235.
So I've got that. V1 is 0, right? So 2 times 1 is 2. 2 divided by 8.5.
Couldn't you just do acceleration times time?
Yeah.
V2
Yeah.
equals V1 plus V2.
Okay, you
What?
could, but what if I got that wrong? Then I messed the whole question up, right? Okay, so, but I would check it. I would check it to make sure I got it right. So anyways, okay, so what's 2? Let's do it my way. 2 divided by 8.5.
0.235.
Did I get the same answer? 1, 2, 3, 5? Okay, perfect. So this is 0.235 meters per second. Okay. So up here, I have 0.235 meters per second. So now I have D, I have V1, I have V2. What do I need to find up here now? Acceleration. So let's find our A. And then I'm going to piece this all together. So I've got V2, V1, D. Which equation am I using? Yes, V2 squared equals V1 squared plus 2AD. And what do I get as my acceleration? Negative
2.02209.
Help me with this again.
Negative 0.2.
You say it right. 0.2.
0.2209.
That?
Sorry. Yeah.
Yeah, perfect. Kept throwing 2's and 0's and 0's and 2's, so we're good. Is that what it looks like? Yep. 2209?
Yeah.
Indeed.
Okay, thanks. I can't hear either, so it's not a winning combination for us, Don. Okay. Alright, so what have I done now? What have I given myself an opportunity to do? Okay, so now that's exactly what I would have done. Now maybe I would have found time, but I don't need the time. Time's irrelevant right now. What do I need to know about forces now? Okay, so I have 2 sections. This section here is the first one, in which there's an applied and a friction force, and a net force. This guy, what is there only here? Is there an applied force in the second section? No. Because he's coasting now. So what is the only thing affecting that skateboard?
Friction.
Friction. So my net force is equal to my friction force. And how do I find net force? Mass times acceleration, so 0.5 times 0.02209 is my force of friction.
Oh,
I'm going to add a negative in there because he's slowing down, right? So what's my force of friction?
Negative .011.
A little louder, Rory.
0.0110.
Okay, thank you. So there is my frictional force. Okay? So far so good? So why did I find that? Well, I have to use that in equation 1 now. Force net equals force applied minus force of friction, right? Okay? I have 0.5. What was my acceleration in the first part? 0.0277. Equals my force applied minus my force of friction. What was the force of friction?
0.0110. Negative.
All right, now here's the part. This is the part that gets... All right, now normally in the textbook they would say add. And then you put your friction down as a negative value. I like to just say, logically speaking, can I tell what I needed as a negative and what I need as a positive? Because it'll make it a lot easier when we get into more complicated friction questions or pulley questions. So it's easier if I just write it like this. Anything that restricts my motion, I just subtract it. Don't put the negative sign in there, just subtract it, and then I don't get the signs messed up. So now, how do I solve for force A now? What do I got to do?
add that to the other side.
Add this to this side. And what do I get?
0.02485. 0.02.
0.02.
0.5.
Thank you. There's your answer to the question. Okay? So again, when I'm looking at this question, I go over to here. I treat it the same way that I treated all the stage questions in kinematics. Find the missing pieces of information. And then how do I apply it to my force? And that's what I do now.
So, okay. So the
Okay?
negative 0.011 was the frictional force.
Yeah.
Opposing its motion.
Right there, yeah. Okay? That question there is a little bit on the tougher side as well. We looked at a couple yesterday that are tougher. That would be one of them. All right?
I've got a few questions. How exactly did you find the acceleration?
Morgan.
I would think